All right, hello everyone, and welcome back to Perceive 2021. Please give a warm welcome to our distinguished guest, Danny Lange. He is the Senior Vice President of AI at Unity. And Mr. Lange will be speaking about AI, synthetic data, and smarter robots. Dr. Lange, welcome to our stage.
Thank you very much. I've been looking forward to this event. And I would also like to thank Matt Seiler and his team for giving me this opportunity to speak to you. As you just heard, I'm going to talk about how AI and synthetic data is helping us making autonomous systems and robots smarter. So I have an exciting presentation in store for you. So let's get going. So very quickly about Unity Technologies, just in case you don't really know about us, we are a real-time free platform. So real-time means that it's sort of, 30 to 60 frames per second rendering of 3D environments. You can think of us as the foundation of the metaverse, the concept of virtual reality blending in with reality. We are primarily making our impact in gaming, in AR, VR. You also see us in automotive and robotics. We are currently covering about 70% of the game market. So it means that about 70% of all video games are made on the Unity platform. We installed on over 6 billion devices. It's some really big numbers. Over 3 billion people play a game developed on the Unity platform every month. And we're about 5,500 employees headquartered in San Francisco. Yeah. So we have an AI team. I lead the AI team at Unity. It's a pretty big team. And our vision is to enable organizations of all sizes to create, deploy, and unlock the value of AI, particularly focus on computer vision, robotics, and what we call spatial or 3D simulation. And this is what I'm going to show you a bit about today. If you think about it, we're a game company. Games have been used to drive AI research for a very long time. It started out with board games. Over 70 years ago, Claude Shannon published a paper on programming computers for playing chess. That was the very first endeavor into using a board game to advance the art of artificial intelligence and computer science. It took a while, but up through the 80s, we saw the world champion in checkers becoming a computer. When I was at IBM in 97, IBM Deep Blue defeated the world champion in Garry Kasparov in chess. And later on in 2011, IBM Watson won over the best players in Jeopardy. If you think about all these examples here of various kind of games, the solution was to have really smart software engineers having the insights to implement algorithms that would be able to succeed, whether that was checkers algorithms or chess algorithms, or in the case of Jeopardy, really a very efficient database lookup of questions and answers that were curated by a team of 300 people before the competition. Yeah. But sort of in the late 2010s, we see a change. We see DeepMind's AlphaGo defeat the world champion in Go, maybe 10 years ahead of its time. Nobody expected it to be possible at that moment in time. And with AlphaGo and its successors, AlphaZero, these systems are based on generic learning algorithms. So they basically learn to play this game through self-play. So it's less about the smart software engineers with insights into chess or Go, and more about learning through self-play. And that has really inspired a whole new generation of AI research based on video games. So we have seen the Atari games play a role both for DeepMind and OpenAI. We have Doom, we have Quake 3 that DeepMind did work with. Minecraft, Microsoft has done a lot of reinforcement learning around Minecraft, StarCraft, collaboration between DeepMind and Blizzard, Dota 2, etc. Yeah. So what is it that these video games they bring to the table? Yeah. I see it as really 4 dimensions of AI. Number one, the visual component. Yeah. So all of these games, they bring 3D rendering to the table. There's something about seeing and acting upon what you see. So it's really a perception challenge that is one of the 4 dimensions of AI. Let's move on to the physical component. Typically in many games, there's gravity, there's collision, there's some kind of inertia taking place. Yeah. So you have the role of physics. So not only do you see, but you also have to understand that there's a surface you walk on, there's gravity in place. Yeah. That's the second dimension. So we've got visual, we've got physical, and then we've got the cognitive aspect. In many, many video games, there's some kind of challenge, some kind of problem that you need to solve to get to the next level or score some points or something that you need to overcome. It's not just enough to run around and shoot and jump, but you also have to solve tasks. Yeah. And the final aspect is the social aspect. It's NPCs in games, so non-playing characters, yeah. So they are like the robots, the agents in the game. There may also be other players playing in a multiplayer game. So there's advanced social aspects of games as well. So you put all these 4 together, and you actually have something that is very interesting. So you have the spatial environment, you have the graphical rendering, you have multi-sensory system, you can have cameras, you can be placed in different places in the game, you have the physics. Well, in sense, you have a controlled, self-sufficient ecosystem that replicates a part of the real world. So in many ways, Unity is your private AI biodome. It's your game engine is the thing that you can create a replica of the real world, and you can start playing out simulations. And that's where we actually start thinking about the concept of the metaverse, which is this virtual environment, this virtual universe, but is closely tied to the real world. And you sort of have a situation where the real world and the metaverse, the synthetic or virtual world, they blend together. And that's what I'm going to talk a bit about today. So we can take this from many different angles. I'm gonna talk about simulation, and in particular about simulation for building autonomous systems. And by autonomous systems, I mean systems that can be robots, can also be smart cameras controlling traffic. It can be systems that basically use perception. So they use, eyes to basically sense the environment or perceive the environment, sensors, machine learning models that help with object detection, etc. And then the second aspect of autonomy is the control. Many, many different ways to implement control. You can just write some code, or you can have rule-based systems that will tell a robot or a smart system, an autonomous system, what to do under given circumstances. What I'm going to focus on today is reinforcement learning. Is one particularly interesting and novel way of controlling autonomous systems. Yeah. So perception and control, that's the 2 elements of the I call that the anatomy of an autonomous system. Yeah, perception and control. So let's talk about perception first. So that's the computer vision. And when we say computer vision, my examples today are going to be mostly on normal cameras and LiDAR, but computer vision is really a broad term for for perception. It can be infrared, it can be depth, it can be radar, sonar, it can be many, many different kinds of sensors. Yeah. So building computer vision models is actually pretty difficult. Yeah. It's have to collect data, you have to hand label it. It really is challenging. If you want to run a robotic simulation, robots, they kind of move slow and they break. Yeah, you have a lot of complexities between these mechanical components and the real world. Bring machine learning into it and gets even more complicated. And then on top of all of that, you have privacy, safety, and regulatory compliance hurdles that makes it really, really hard to use real world data. Yeah. And then you have to do this at massive scale. Typically, you need a lot of data to build these systems. Yeah. So what we've been exploring at Unity is this idea of using synthetic data for solving computer vision challenges. Yeah. So you can produce a very high volume of data at very low cost. You really need to create a single 3D model, whether that is of a tent or shoe or some food. You have the 3D model, and after that initial cost or investment in creating the model, you can now, using parallelism, you can use cloud environments, you can generate vast amounts of varied data over that asset. Yeah? And you really only pay for the resources that are consumed in creating that. Yeah. So at the end of the day, synthetic data gives you a set of very interesting advantages when it comes to creating these training data for computer vision systems. Yeah. I'm going to show you an example here of what we can do in creating bounding boxes, 2D, 3D bounding boxes, instance segmentation, semantic segmentation, and more importantly, use procedural placement for creating domain randomization, randomize on the materials, the lighting, in just endless amount of combinations. Yeah, you can do that in a warehouse environment. You can do it with retail products, or you can do it, outside in a city environment or street environment. Yeah. So I want to show you a small video here of one of the many tools we have. In this case here, it shows you an engineer working with a training set. There's a lot of generated synthetic data. There's a lot of confusing backgrounds to make the model stronger. But more importantly, what I show you here is essentially the perfect label set along with the visual data. So it's a JSON metadata set that is generated along with images that you then can use to train your machine learning model. And in this small example of an autonomous vehicle simulator from LG based on Unity, we show you there were some depth examples, RGB, in this case it's LiDAR. So you basically have a multi-sensory ability to generate training data. So that was the perception part very quickly. Let's move on to the control part, where I'm going to show you some examples of reinforcement learning. You want to have robots, not just one robot, multiple robots to collaborate together to solve problems. You may even have humans in there. The robots are coming out of the cages, out of the manufacturing cages, where we are primarily seeing them, into more collaborative environments. That raises some challenges because it's really hard to program robots to take these very complex environments into account. So with reinforcement learning, which is a method of training systems for control, is becoming increasingly popular. You have the idea of a system observing or perceive the environment, taking some action according to a policy, and then reap the rewards or the penalties from that. And then as the system spins in this flywheel, it gets better and better at figuring out how to get the positive rewards and avoid the negative penalties. Yeah. So over time, the system moves from an exploration mode to an exploitation mode. Yeah. Interesting enough, this is the most used algorithm at Amazon. Yeah. The system that shows you products and figure out which products you like, products you purchase, and which you don't like and do not purchase. And then over time, Amazon is able to move you towards the exploit, show you stuff you really want. Netflix is the same, YouTube is the same, Facebook is the same. It's this wheel that optimize for positive rewards. Well, you can use this in our settings as well. So just for an example here, we want to program a computer or train a computer to see if it can learn to have the chicken safely cross the road. Yeah. So we observe the pixels, we go left, right, forward, backward, and then the reward signal is negative for being hit by a car and positive for picking up a gift package. Yeah. And if you look at the chicken now, take a look here. It initially, very first training phase here, it's moving randomly around, as much backwards as forwards. But in a moment, it will hit the package up there on the right. Yeah. And then get killed. So after just 1 hour of training, basically trial and error, or as I like to say, try and succeed, the chicken figures out to pick up gift packages. They were positive events, it's rewards, and then it avoids a few cars and then gets hit. So it's not really good at avoiding the cars yet, but it is very impressive what happens after just 6 hours of training. The chicken has now become superhuman. Yeah? It will pick up gift packages. It will avoid the cars. And all these cars are coming in completely random way. It's never seen it before. So it has developed the capability to survive the traffic starting from scratch. Yeah. So we can apply that to have 2 agents learn to play some kind of racket play together here. Same way, we can have agents, 4 agents playing against 4 agents on 2 teams, some kind of indoor soccer. You see that they develop some very interesting behavior just from playing, millions of games over and over. They develop this idea of having a defensive player, or more like a goalie, staying behind, defending the goal while 3 other players are playing in an offensive mode. Nothing that we programmed in here. It's just emergent behavior, having these agents training from scratch. Yeah. Well, you can use the exact same technique to train a robotic arm to touch an object that are placed randomly on a table. Yeah. So you have a lot of complex joints here that needs to operate in certain patterns to touch this object. You can learn that through reinforcement learning. What we did in Unity is that we made it easy for you to import robots directly into the Unity platform. So we support URDF that allows you to take an industry description of a robot and then basically import it and have it appear in your Unity environment. Yeah. And it now allows you to simulate the robotic movements. Here's pick and place, and then move that, transfer that learning directly to a model that controls a physical robot in our office. Yeah. And of course, you can move on to industrial robots and more accurate physics, as we do in this example with the Algorithms physics engine that mimics physics at industrial level quality. So, as I said, AI is progressing using these techniques. Yeah, and the reason it is so important to take a look at synthetic data is that that we experience a rapid exponential growth of the use of data in AI. My observation over the past decade is that somewhere between every 18 to 24 months, the amount of training data doubles. So in many ways, the world is running out of data. In the real world, you can't gather that amount of data that you actually need. Sorry, and therefore, synthetic data is the solution. You need to complement your real world data with synthetic data. Yeah. So let's get the perspective in place here. A game is running at 30 to 60 frames per second. But when I talk about a simulation, when I talk about generating data, I don't have to restrict myself to what humans are able to capture. Yeah, I can run at unlimited frames per second. Yeah, your life in 1 year at 30 frames per second is actually 1 billion frames. Okay, so I can basically accelerate time if I can run faster than 30 frames per second. Yeah, I can also deploy or use massive parallelism, so I can run on 10, 100, I can run on thousands of servers in parallel to speed up that frame rate. Yeah, I can also, with synthetic data, of course, in real time influence the data being generated so that I can optimize my model development. Yeah. So here's an example of a robotic hand. This is from OpenAI. And you see the camera up on the right. And basically that camera is looking at the position of the hand and the cube. And it is that perception is going through a model that controls the hand. That model was developed using Unity. It took 300 billion simulated frames to achieve this. That's the same. Think about it. That's the same as 300 years of experience. Yeah. We could make it a little more complex. We can solve Rubik's Cube instead. So single-handedly tweak the cube. That process using Unity to generate synthetic data required 10 trillion simulated frames. So that's 10,000 years of experience to learn, to train this hand to do that job in the real world. Pretty fascinating. Of course, scale matters here. We want to generate data that reflects different weather patterns, different situations, in this case, different traffic situations. We want to generate that at massive amounts to build autonomous systems. Yeah. So everything I showed you, we have a lot of background information. For developers, we have GitHub repos that you can freely access for synthetic data generation using our perception package. We have packages for you to use the robotic operating system Rasa. So Rasa packages that basically provide standard access to robots. And we have the ML agents framework that allow you to develop reinforcement learning scenarios. So I showed examples of all of these packages that are freely available. We also have some sample data sets. We have a home interior data set, and we have a retail data set that you can download and play around with. And for more information, we have a computer vision landing page. We also have a robotic simulation landing page where you can go and learn more. And for those who wants to get sort of under the hood, we have 2 papers published. One is on the perception work we have done, how to generate synthetic data for computer vision. And then one on ML agents, a general platform for intelligent agents. I encourage the people who want to dive deep can go and download these papers and check it out. Yeah. So that was all I had in store for you today. Feel free to connect with me, Daniel Lange, on Twitter and Danny Lange on LinkedIn. I hope you enjoyed it. I surely did. Thank you very much.
Thank you so very much, Dr. Lange. What an excellent presentation. Fascinating topic, certainly something we deal with a lot here at Clarifai. Where do we get the training data from that we train these models with? So thanks again. We've got a resounding sound of applause from our virtual audience. And we will see you at our next session. Thanks a lot.